Hello, my name is Colin Go, and I'm from Section C of Physics 2211, and I'll be discussing Lab 4 oscillations today. So the purpose of this lab was to compare the predicted and observed motion of the mass using tracking software and a computation model, as well as plotting the energy changes computed from that model. Just quickly, a results preview here, we have our outputted x position and y position versus time graphs, and you can see that our model, which is in the blue, and then our experimental or observed data, which is in the red, they're quite similar on both counts. There's some slight deviation, which we'll elaborate on later. Additionally, we plotted our energy change right here. You can see it does represent the energy principle. We'll get into that later as well, where the this orange line shows a zero change in total energy. And then, so our introduction to some physics fundamental principles, we have Newton's second law and the energy principle. So we'll start with Newton's second law, which F net equals ma. F net also equals the change in momentum or the change in time. And for the purpose of this lab, we have F net equals gravitational force plus spring force. And then after that, we substitute in gravitational force and spring force with their respective formulas, and we end up with this equation right here, which we will use in our code as well as to find the L length. Energy principle, initial energy equals final energy because delta energy equals 0, delta of energy, the change in energy equals 0. We use this later in the code as well, and then we also have our velocity update formula as well as our position update formula, which we use in the code additionally to update the masses movements for our plot. Some useful other formulas that we have include kinetic energy, we have potential gravitational energy, potential spring energy, and the period of springs, which we use to find K. Our lab setup, our materials were the spring, the rope, the mass, the tracking software, and GlowScript. Our assumption is that the system is isolated, so no external forces are impacting, including air resistance. The system itself is the mass, the spring, and the earth, and everything else. The surroundings is nothing else, sorry. And the units is meters and seconds. So here's our lab setup. We have our fixed attachment point with the spring, the rope down here connected to the mass. We also have our axes right here, where down is the negative y direction and right is the positive x direction. Here's our tracking software. You can see our data and our plots to the right here. And then our initial conditions, we have the mass, labeled ball here, is 0.402 kilograms. And then our initial position of the mass is negative 0.109 and negative 0.641 in the x and y direction respectively. And then our mass has a initial velocity of 0 at rest. So to find the spring constant, we wanted to take a look at the y direction graph and find the average period of these 4 periods right here. And so that ended up being 1.5195, and then we use this period with this formula, as mentioned earlier, to find the spring constant K, which is 6.874. And so we plug that into here in our code. We also have 9.8 as our gravitational force constant, and then our relaxed length of the spring, which we found using Newton's second law, that formula that we derived, as well as the K constant we found in the previous slide. We also have to calculate L hat, and S, which is the displacement of the spring, using these respective formulas, and then we also substituted the energy formulas that we went over in the previous slides for these variables right here. And so we entered our computational loop, we defined our energies, and then we have to define F grab, F spring, F net. So we F grab equals negative mg, the spring, negative ks, s times L hat, which we found earlier, and then our F net from before, we can see that it's the sum of the spring force and the gravitational force. We also apply the momentum principle, the update formulas for velocity and position to help us graph our data as well. We're still in the loop here, and we basically substituted all the formulas in that we found earlier. We also found the deltas of each energy by subtracting its initial energy. And so this is our code, and then we ran the code and we found these two graphs here. So as you can see, our x graph, quite similar still. Our red is experimental, our blue is model. They're pretty similar in terms of their dips and their peaks. There's some slight deviation because of sources of error here. So one source of error is the external forces, including air resistance that we assumed weren't there to begin with, that might have impacted the data, as well as human error in terms of center of mass tracking with our software. And then we also assumed that this was an ideal spring, which if it was not an ideal spring, then that could have also impacted our data. So what does it mean? Yes, it does follow our energy principle. You can see our energy is conserved. You can see each graph, it cancels out its respective graph here, and so our total orange line shows that there's 0 energy change. And then the second part, for what does it mean? we took a look at the periods of x and y position graphs. We found that the period of the x position graph was 1.6618, and then we found a k constant of 5.747. And we did the same thing earlier for the y position. We found that we had a smaller position, or smaller period, and then a larger k constant. So our conclusion here is that we see that from x to y, we have a different direction, which equals a different constant, which affects our total graphs because they have different periods. So just as a conclusion, we found comparisons between the predicted and observed data, and we saw our energy principle being conserved. Thank you.